Today I will explain about breadth first search. This is another variant of the graph algorithm. So in the graph, there are some other kind of concepts that we need to know. First is about path graph. So what is path graph? Path graph is a kind of linear graph. Okay, we call it linear. It is a path with at least two vertices is connected and has two terminal vertices. So what does it mean? I think you know path. Okay. A path is a traversal from one vertex to another vertex, and then we have a path with at least two vertices is connected. So at least two vertices, then it means 1, 2, at least two vertices, and has two terminal vertices. What does it mean, terminal vertices? So the terminal vertices means vertices that have 1 degree, degree 1. It means I have one vertex and then I have one edge. I have one vertex and then I have one edge. So this is the terminal. So you can imagine the same like the bus terminal. In the bus terminal, yeah, we have only one edge. So every bus will go to the terminal and every bus will go from the terminal. Then it means we have one edge into the node or into the vertex, and we have one edge outgoing from the vertex. While all others, if any, have degree 2. Okay, so it means the degree can be 2 or maybe more than 2. So for example, this is a graph. Okay, this is a graph, and this is a path graph. So this path graph means I have one vertex with degree of 1. I have another vertex with degree of 1. But this vertex and this vertex have degree of 2. So this one is 1 and 2. And this one is 1 and 2. Okay. If it is more than 2, then we can say that will be a kind of the spanning tree. But if it is path graph or linear graph, we have only 2. So like this one, it is only 2. So this is the path graph. Paths are often important in their roles as subgraph, as of other graph, in which case they are called as paths in that graph. So I can say this is one path. We can have another path. We can have another path, and so on. We have another variant, we call it bipartite graph, or we call it pie graph. Bipartite graph or pie graph is a graph whose vertices can be divided into two disjoint and independent sets. So in this case, I have U, and then I have V. So there are two independent sets, such that every edge connects to a vertex in U to 1 in V. So this is a vertex in U. This is another vertex in V. And then it is the edge. So the edge is connected from one vertex in U and is connected to one vertex in V. Bipartite graphs are used extensively in online space. Especially it is for the search advertising and e-commerce for similarly ranking. In the formal definition, bipartite graphs is denoted as G. We have U, we have V, and we have E, where U and V are the set of nodes, and E is the edge, the set of edges on the graph. What does it mean? For example, this one. If you buy an item in the online shop, let's say you can connect to Kupang or Gmarket and etc. So I want to know the user one buy the item one 5 times, for example, or the user one give the rating to item one 5. So that's kind of things we can put into the bipartite graph. So in this case, for example, it is 1, 2, 3, 4, 5. And then let's say this is item 1, 2, 3, 4. Then the user one give the item 1 rating 5, for example. The user one give the item 2 rating 1. So the rating, if it is 1, then maybe the product is bad. This is rating 0. Rating 0 means this user has never bought this product. The user one has never buy this product. Then we can make the graph like the bipartite graph. For example, the user one connects to the item one, and then the rating is 5. The user two connect to the item 2, and the rating is 3. And the user one connects to the item 2, and the rating is 1. Then we can see that, okay, the most popular items in this case is item 2 and item 3, because there are 2 users. There are 2 users. Item 1 has only 1 user, item 4 has only 1 user. There is another kind of graph, we call it graph structure stack. So we have the graph and we combine with stack. So a graph structure stack, GSS, is a directed acyclic graph. Okay. Directed. So it means we have a direction. Acyclic. Acyclic means no cycle. Okay. And then it is a graph where its directed path represent a stack. So when we have this direction, when we have this direction, we have this direction, and we have this direction, it is represented as a stack. For example, I have 4 stacks. So the first stack is 7, 3, 1, 0. So I have 7, 3, 1, 0. The other stack is 7, 4, 1, 0. So 7, 4, 1, 0. And this is the direction. The other is 7, 5, 2, 0. 7, 5, 2, 0. And the other is 8, 6, 2, 0. 8, 6, 2, 0. Okay. So what does it mean? Okay. So in the applications, we can look at the grammar. Okay. So in this kind of grammar, you have a sentence like this one. The little boy ran quickly. Then it is adjective. Little, it is another adjective with a singular noun. So we want to combine this little boy as a noun. And then this adjective and this noun has been combined into another noun. This is a singular verb and this is an adverb. So we can combine those two into a verb. Then it becomes one sentence. Then this is the stack. This is another stack. This is another stack. This is another stack. And this is another stack. So we can put this kind of grammar, or we call it, this is the graph structure grammar, as a graph structure stack. So in the previous chapter, we learned the graph traversing using BFS. So we have the depth first search to understand the graph traversing. So the idea is the same with the graph traversing using stack. So you can also use stack for the traversal. For example, let's start with some vertex S. Okay, so this is the starting vertex. And then let's visit the first neighbor of S. Okay, so let's say the first neighbor is T. Okay. Then visit neighbors of that neighbor. So let's suppose I visit U. Every time, consider the neighbors of the last vertex visited. So you can consider, let's say, after V, you visit the neighbor of T, which is U. You visit the neighbor of U, which is W. And then you visit the last vertex, which is X. Then you can put, let's say I consider the first vertex, which is T. Then I put into the stack. And then I put the next node, which is V. So I put into the stack, into the second. Let's say now I have U. So I put into the third. And then let's say I have now W. Now I put W. And the last is X. Then I put X in the line. In order to find the path, or in order to find the spanning tree, then you can push and pop. Okay, so this is push. It means you want to push the data into the stack, and then you can pop. If you pop means you remove the data, or you remove the item from the stack. After you remove this from the stack, then okay, the last vertex is X. And then after X, I can visit W. And then after I visit W, so I can consider the U. So we can check whether U and W is connected. If it is connected, then we can just make the connection. And then we check the V, whether it is connected to U or the W, and so on. We can also do the graph traversing with Q. So if we do the graph traversing with Q, means we use the concept first in, first out. Okay, if you still remember, the Q is the first in, first out. If we do with the stack, it means we do the last in, first out. Okay. Now, if we do with the Q, let's say we have the same. graph, and then I visit S, and then visit the neighbors of neighbors in turn, S, and then I'm going to visit T. After T, I'm going to visit U. So I'm going to visit W. I'm going to visit V, and then the last one, I'm going to visit X. So you can put into the queue, and then you can remove after you put the element into the queue. So this is the graph traversing with queue. Okay, queue is using the first in, first out concept. Now let's look on the details about the breadth first search. We call it breadth first search or BFS. If it is depth first search, so we use the DFS. BFS is a general technique for traversing a graph, and a BFS traversal of a graph G, it means we do this following. The first, we visit all the vertices and edges. Okay, so the same with the DFS. We visit. And then determines whether G is connected. Computes the connected component of G and compute the spanning vertex of G. So we learn about the spanning tree, spanning graph, and we also learn about the spanning vertex. BFS on a graph with n vertices and m edges. It will run O(n) plus m. So n means the number of vertices, and m is the number of edges. BFS can be further extended to solve other graph problems. For example, you need to find a path with the minimum number of edges between two given vertices. Or you want to find a simple cycle, if there is one. So the idea is similar with the DFS. Now, this is the algorithm of BFS. At the first, the BFS, we have a graph, and the output is the labeling, whether the edges and the partition of the vertices of G. So let U be all the vertices from the graph, and then set the first as unexplored. And then let E be the edges of the graph, and set all the label as unexplored. And then for all the vertices, if the label is unexplored, then do this function. Do this BFS. So the BFS, there are two parameters. The first, we have the G, and then next we have S. So what is S? S is now the current node. We have another variable, we call it L. So L0. L0, it is a new empty sequence. And then L0 at last S. So I'm going to add the S, and then we are going to set the label S as visit. So S, let's say S is the starting vertex. Okay, so S is the starting vertex. Then I'm going to put the S as visited for the first time. And then let I be 0 for the first time. So if Li is not empty, so here, what is the meaning? This one is not. Okay. So if Li is empty, then because we have not, then if Li is not empty, now we will check Li plus 1. Li plus 1 equals to the new empty sequence. So I is 0. Okay. Then I plus 1 means L1. L1 will be empty sequence. And then I'm going to check for all the elements of Li. The elements or the vertices will be in the variable V. And then I'm going to check what are the incident edges of V. For 1V, I'm going to check the incident edges of V, and then this is the E. So let's get the label. If the label is unexplored, then check the opposite of the node. Check the opposite of V based on the E. And then if the label W here is unexplored, then you can set the label. So the label E is discovery and the label W is visited. And Li plus 1 will be added with W, with the W. If it is not, then set the label as the cross. So at the end, we will add I with 1. So I, which is originally 0, now it will become 1. And then we will go back here and then again check if Li is empty or not. If Li is not empty, then again we do this one. So let's check with the example. Okay, before we do the example, this is the Python implementation. Okay. So in the quiz, I will give you question like this Python code. And then you can check like this Python code. This is the correct one. So I will give you the question with errors. And then you need to find the errors. Okay, so that will be in the quiz. Now let's check this Python code. Okay, BFS, BFG, and then S, and we have a parameter discover. So the level equals to S. So S in this case, it is a list and only one node or only S. Now I will like to check what is the length of the level. The level length is 1. So it means it is higher than 0. Since it is higher than 0, so I will go in this section. Now next level equals to empty space. Okay, empty list. And then for you in the level, now let's check if the incident, if there are some incident edges of U, so check the opposite of U and then put into the variable B. If V not in this cover, what is discovered? Discover is this one. And it means if V is not in this list, we put discover. So discover means I discover the V and let's the edge that incident to this vertex will be in the list of discovered. And then next level, let's append the V. So we will do this loop. We will do this loop from this E, and then at the end we will return back the level. So the level will be equals to the next level. So let's see with this animation. Okay. First, I will define the blue color as unexplored, and then I define the yellow color as the visited vertex, and the line without arrow is unexplored edge, and then the line with arrow is discovery edge. The line with dash line, it is the cross edge. Now let's assume we start from A. Okay. We start from A, and this is the L0. So let L0 is the new empty sequence, and we want to have this graph. Yeah, this is the graph, and I'm going to start from S. So let S equal to A. Then from the L0 at last S. So in the L0 we have A, and then set the label S as visited, then set the label A as visited, and then I let B equals to 0. Okay. Let I equals to 0. Now let's check L0, is it empty? L0, we have one element, then it is not empty. Now let's create a new empty sequence. So L1, okay, L1 is empty. Now let's check the Li element. The Li element means the Li means the L0. We have the vertex A. Okay, then let V is A, and now let's check the incidence of A. The first incident of A is this X, and then let's check the E. Let's check AB, because AB is the first time to be explored, then originally it is unexplored. So we want to find out what is the opposite of V. The opposite of V based on this X, then it is P. So W now equals to P. Now let's get the label of P. P, because it is the first time to visit P, then of course it is unexplored. So set the label E as discovery. So set the label E. So this is as discovery. So I make this as DE. And then set the label W as visited. Set the label W, which is P, as visited. Then Li plus 1 or L1, let's add it the W. So we put P in L1. After we finish, let's get back to this one, because we have not finished with the all edges from it. So what is the next? The next edge from A is to C. Let's get the label of E. So the label of E here is unexplored. Okay, originally it is unexplored. Now let's get the opposite of V. Let's get the opposite of V based on this edge. Then it is C. So let's look at the label C. Is the label C unexplored? Because it is the first time to visit C, then okay, let's set the label E as discovery. So let's set the AC as discovery, and then set the label W, set the label C as visited. Set the label C as visited. Now Li plus 1, which is I is still in 0. So L1, now we have B and C. Okay. Now L1, we have B and C. So we will return back to this for loop and then check for the next E, which is AD. Okay, before we have still I equals to 0, and then L0 equals to A, and then we have L1, which is B and C. Okay. Then we want to explore A to D. Now we have the E, this is the E, and then check the label E. E is unexplored? Yes. So AD is still unexplored. Then we check what is the opposite of V. The opposite of V via E is D. Then W is D, and then get the label of W. Get the label of D. What is D? D originally it is unexplored. Yes, it is true. Then set the label E as discovery. Set the label E as discovery. So AD is a discovery X. And then set the label W as visited. Set the label D as visited. And then Li plus 1, add the last W. So I'm going to add D into L1. Then we finish with all the nodes in A. So we finish. We already look at AB, we look at AC, we look at AD. Then we finish with all edges. And then let's go back to this one. V, it is the element of L0. L0, we have only A. Then we already finished with all the elements in L0. Then we will go to I equals to I plus 1. Then I will be added by 1. Then now I equals to 1. So we have L0, which is A. And then we have L1, which is B and C and D. And then I, originally it is 0, now equals to 1. Now we will go back to this one. While Li is not empty. So L1 is not empty because we have B, we have C, and we have D. So it is not empty. Then let's set up Li plus 1 as a new empty sequence. So we prepare L2 equals to empty sequence. So I need to check the V, which is the elements for all L1. Okay, I equals to 1, Li element. So we have to check every B, C, and D. Now let's go to B. Okay. B, I need to check what is the incident edges of B. So the incident edges of B, first, let's say this one. So this is the E. Okay. Now I'm going to check, get the label E, whether it is unexplored or not. BC, is it unexplored? Yes, it is unexplored. Then let's get the opposite of V, B, E. Then the opposite is C. So let's check the label of C. If the label of C is unexplored, then do this one. But what is the label of C? The label of C is already visited. Because the label of C is already visited, then we do not do this one, but we do this one. Set the label E as cross X. So BC, it will be cross X, C. Now, let's check. Oh, yeah, I need to write again. L0 is A, L1 is B, and C and D, and then I equals to 1. Because we already finished with BC, now let's check with the other edge, BE. So BE, E is the incident edge of B. Now let's check if BE is unexplored. Yes, BE is unexplored. Let's get the opposite of B. Let's get the opposite of B. It is E. Let's check the label of E. The label of E, is it unexplored? Yes, because this is the first. So we have not explored yet. Then set the label E as discovery. So BE is discovery. And then set the label W as visited. So set the label E as visited. And then Li plus 1 at last. Because we have L2 at the first is empty. Now we put E in the L2. So we return back. Is it finished? BC, BE? Yes, this is already finished. Then we go to the next element. We go to the next vertex, which is C. Now let's go to C. The same with the previous one. C, we want to check with the D. CD originally it is unexplored. CD originally it is unexplored. So we want to get the opposite of C. The opposite of C is D. Then the opposite of C is D. So I want to check what is D. Is it D unexplored? D already visited. Then because D already visited, then we go to the cross. So the edge from C to D, edge CD is the cross edge. And the last one, we want to check the C to F. And then we want to see if CF, the edge is unexplored. Yes, it is unexplored. Let's get the opposite of B. The opposite of C is F. Now let's check the label of F. It is unexplored. Yes, F it is unexplored at the original. So we set the label E as discovery. So CF as discovery edge. And then label F is visited. Then I'm going to put into the L2. So L2 is E and F. And then we go back. Is it already finished with C? Yes, it's already finished. Now let's move to the next node, which is D. Visit to the next node, which is D. In the D, we check what is the incident edge. So we have this incident edge, and then get the opposite of V. Get the opposite of D, which is F. Then let's check. If the label of S is unexplored, F is already visited. Then it means we will set the label DF as a cross edge. So it is not discovery edge, but it is a cross edge. So we finally finish with everything. Then we can do the analysis. Okay, let me stop here. I will explain more the analysis after the break.